Let's take a look at the kinetic energy for an object that is rotating. We're going to take a look at a single point, this point right here, on a rotating disk, and that disk is rotating with an angular velocity of omega. We know that from before that the kinetic energy for this particular point is going to be given by the equation 1/2 mv squared. But we know that velocity tangential, that linear velocity that that object or that point is moving at, is equal to r omega, the radius times the angular velocity. So this r here. What we can do is we can go ahead and substitute in. So what we'll get is that kinetic energy for that spot that's rotating is going to be equal to 1/2 times m times r omega squared. So that gives us kinetic energy is equal to 1/2 m r squared omega squared. But we know that mr squared is the moment of inertia for our object. So what we wind up with is that rotational kinetic energy is going to be equal to 1/2 times the moment of inertia times the angular velocity squared. So that is our rotational inertia, or excuse me, rotational kinetic energy. That rotational kinetic energy just becomes part of our total mechanical energy. So rotational kinetic energy can be included in the total mechanical energy. And what we get is that our energy, total mechanical energy, is going to be equal to 1/2 mv squared. That's the object's translational kinetic energy, plus the rotational kinetic energy, plus the gravitational potential energy. So rotational kinetic energy is just another portion of our energy that we have to be concerned with.